Think about the world around you for a second. How hot is it? How far away is that building? How fast are you driving? We're using numbers to answer these kinds of questions all day, every day. But have you ever stopped to think about where those numbers get their actual meaning? Well, that's what we're going to dig into today.
So let's try something. If I just throw a number at you, say 50, what does that even mean? Is that hot, cold, fast, slow? Is it heavy or is it light? Without any more information, it's just a number. And honestly, that's a problem.
Right, by itself, a number is just pure confusion. It's like a symbol just floating around in space with absolutely no anchor to the real world.
But watch what happens when we give it a buddy. 50 kilograms. Okay, now we're talking about weight. 50 kilometers. Now that's a distance, a journey. 50 seconds. Well, that's a period of time. All of a sudden, that confusing number tells a story. And that is the incredible power of a unit.
So, our first big step here is to understand exactly how we give these numbers a job to do, how we connect them to reality. And the tool we use for that, the key to the whole thing, is the unit.
So what is a unit officially? Well, it's basically a standard reference point that we all agree on to measure something physical. The kilogram, the meter, the second, it's our shared language for measurement.
This quote just nails it, doesn't it? Without that little kg or km, our number 50 was totally lost. But with a unit, it becomes useful information, something we can actually act on. That's why they are absolutely essential.
And this isn't just some neat trick for daily life, this is the very foundation of physics. I mean, what is physics really? It's the science of studying things that can be measured, what we call physical quantities. So if you want to understand the universe, you've got to start by understanding units. There's just no way around it.
Okay, but it can't be the Wild West, right? We can't all just make up our own units. That would lead right back to confusion. For this whole system to actually work, our units have to play by a clear set of rules so they're reliable for everyone, everywhere.
So, what makes a good unit? Well, there are 4 key things. It's got to be easily available so anyone can use it. It has to be universally accepted so we're all on the same page. It needs to be reproducible so we can all make accurate copies. And maybe most important of all, it must be invariable. A kilogram in Paris has to be the exact same as a kilogram on the moon. It can't change.
Let me give you a simple example. Let's say you have 10 kilograms of rice in Mumbai. Now, you hop on a plane and take that same bag of rice to Delhi. Guess what? It's still 10 kilograms. The location changed, but the unit, the kilogram, stayed constant. That's what makes it a reliable standard.
So once we have these reliable units, the next logical step is to organize them into systems that make sense. And this is so important. A simple mix-up in units once caused a multi-million-dollar Mars orbiter to crash into the planet. So yeah, getting this right really matters.
Over the years, there have been a few big systems. There's the CGS system, which uses centimeters, grams, and seconds. You've also got the FPS system, using feet, pounds, and seconds. And then there's the MKS system, which uses meters, kilograms, and seconds. See? They all measure the same fundamental things, length, mass, and time. They just use a different yardstick, so to speak. And while you might see different systems used in daily life, the global scientific community has pretty much standardized on one, the SI system, which is that MKS system we just mentioned. You can think of it as the universal translator for scientists, making sure everyone's calculations line up, no matter where they are.
And now we get to the final and maybe the most elegant idea of all. It turns out that all these units and all these systems are used to measure just 2 basic types of quantities, and these act as the fundamental building blocks for all of physics.
So on one side, we have what are called fundamental quantities. Think of these as your basic Lego bricks. They are totally independent. They don't rely on anything else for their definition. Length, mass, and time are the classic examples. And then on the other side, you have derived quantities. These are the complex, cool things we build from those basic Lego bricks. Things like force, work, and energy, which depend completely on those fundamental quantities.
Here are the heavy hitters, the most important fundamental quantities, along with their SI units. We've got length, measured in meters, mass in kilograms, time in seconds, temperature in Kelvin, and electric current in amperes. It's kind of wild to think that almost everything else in physics is built from just these few core ideas.
That's a great question. How exactly do we build something more complex, like force, from those simple fundamental blocks? Let's actually break it down. Okay, so let's follow the chain. We know from physics that force equals mass times acceleration. So force depends on mass, right? And what is mass? Well, that's one of our fundamental Lego bricks. Easy. But it also depends on acceleration. So what's acceleration? That's just a change in speed over time, which really means it's derived from length and time. So since force is built from these other quantities, it's a derived quantity. See how it all connects back?
And that's really the beauty of it all. From just a handful of fundamental units, we can create a system to describe and measure pretty much everything in the physical world, from the force of gravity to the energy of a star. It's this incredibly elegant way of turning chaos into clarity. And it really only leaves one question. What will we figure out how to measure next?